All right, so this lesson is about forces. Okay. When you apply force to an object, you change its motion, meaning you change its velocity. So you might have seen this. This is Newton's second law of motion. When you apply a force to an object, you give it acceleration. Okay? All right, so we'll learn all of that. Okay. So again, you come across this name on this course, Dr. Feynman. So here's a quote from him at the beginning of this chapter. The first principle is that you must not fool yourself, and you're the easiest person to fool. So just he's saying question everything in science. Okay. All right, this is Newton. He's a towering figure in science. He gave us the laws of motion, which is what we'll start this chapter by studying. Okay. He also discovered the law of gravity. He invented calculus, and he gave us theories of light and color. Okay. So he did many great things. And so justifiably, he's a towering figure in science. Okay. So here's Newton's first law of motion. Okay. What this says is the following. Let's say you push an object like this. What Mr. Newton says is if you push an object like this, give it a velocity, it will maintain its velocity forever if no force acts on it. That's what Newton said. But this thing stopped. So what Newton is saying is, if I push this, so for instance, have you guys played air hockey? You get the puck moving, and the puck will keep moving. It will maintain its velocity. So what's the difference between that and this? I'm sorry?
Gravity?
Well, there was gravity acting on the puck here.
Okay, so there's air coming.
So it's friction that stopped it. Okay? And so in air hockey, to keep it moving, you remove friction. Okay, so this is the neat thing about Newton's first law. He realized that if no force acts on it, so for instance, if you went into space and threw a baseball at 95 miles an hour, and if there was no object near it, it'll keep going at 95 miles an hour forever. Okay? All right, so that's Newton's first law. So the object will remain at rest if it was at rest, if the forces acting on it are zero. Okay? Or maintain a constant velocity if it was moving. Okay? All right, so this is, the first law says what happens if the net force is zero. Okay? Now the second law says what if the net force is not zero? If the net force is not zero, then the object accelerates. And this is Newton's second law. Okay? The greater the force, the greater the acceleration. All right. And also for a given force, the greater the mass, the smaller the acceleration. Okay. All right, so let's look at units. We'll mostly work in SI units. Okay. So mass is measured in kilograms. So mass is measured in kilograms. Acceleration in meters per second square. Okay. So the units for force are kilograms, meters per second square in SI units. And in physics, when you have a combination of units, you don't want to be writing this all the time. Okay. So we give it a special name. And generally, the combination of units are named after scientists who worked in that area. And we call it a Newton in honor of Mr. Newton. Yep. So forces, the units, SI units for forces are newtons. Yep. In everyday language, in everyday usage, we use the pound for forces. Okay. But in this class, we'll use the SI unit, Newton for forces. Okay, so the first law says what happens if force is 0. Okay, then your velocity does not change. The second law says what if the force is not 0? When the force is not 0, you accelerate. Okay. Here's what the third law says. Okay. If you exert a force on any object, okay, so if you exert a force on any object, that object will exert an equal and opposite force on you. Okay, so Newton's third law says action. So here's another way of stating it: action and reaction are equal and opposite. So, for instance, this girl is exerting a force on the wall, and the wall pushes back on her, and that's how she moves forward. Okay. In fact, that's how you walk as well. So, for instance, when you're walking, what happens is you're pushing back on the ground, and if your foot slipped, you couldn't walk. Okay. So, and the friction force on the ground is what's pushing you forward. Okay. So that's how you walk. All right, so here's a case where friction is useful. Yep. You guys following this? Okay. All right, so now we'll talk about what happens if there are multiple forces acting on an object. Okay. So on this lady, here's this person pushing on her, here's this person pushing on her. Okay. The net effect on her is the sum of these two forces. So this force is that, this force is that. The sum of these two forces is that. Okay. So now what the superposition principle says is, okay, I'm going to draw this lady like that. Okay, so the superposition principle says the following. If these two forces act on her, and if this single force acts on her, you can't tell the difference. Okay? The effect is the same. Okay. And that's true if there's a million forces acting on her. If there's many forces acting on her, and a single force that is the sum of all those forces acting on her, you can't tell the difference. Okay? And that's the superposition principle. So when several forces act on a body, the effect is the same as that of a single resultant force. Yep. And by the way, so mass times acceleration, so this is Newton's second law. So if an object's mass is 1 kilogram, and if its acceleration is 1 meters per second square, then a force of 1 Newton acts on it. Yep. All right, so here's a simple example. I'll go over it. You probably have a similar problem on the test. Okay. Just the numbers will be different. All right, so this problem says 440 gram can of food is given a shove on a frictionless level surface and is observed to accelerate. So this is a frictionless surface. It's observed to accelerate at a rate of 1.5 meters per second squared. What is the force in newtons that was applied on the shove? Okay. So you applied this force, and its acceleration was 1.5 meters per second squared. Okay? And you want to calculate the force. Well, first thing you have to do is convert the mass from grams to kilograms. Okay? And here's the conversion. See, 1 kilogram is 1,000 grams. So 1 kg divided by 1,000 grams. See, this divided by that is really unity. That's 1. So you can multiply that. You can multiply anything by unity. Yeah. So that's how we'll do the conversion. By the way, 440 grams is a soda can well, 440 grams is a pound. Okay, 454 grams is a pound. So this is 0.44 kgs. Okay. So the force is 0.44 kg times the acceleration, 1.5 meters per second squared. 1.5, half of that is 0.22. So 1.5 times that is 0.66 newtons. Okay. So fairly simple problem. When you want to calculate the force, just multiply the mass times the acceleration of the object. Okay. So there'll be a problem like this on the test. The numbers will be different, that's all. I'm just getting closer to the coffee. All right, so Newton's law of gravitation. Okay, what Mr. Newton realized was that every object in the universe attracts every other object. And the magnitude of the gravitational force, the strength of the gravitational force is given by this equation. Okay. This is called the universal gravitational constant, meaning it's the same for all two objects. It's the same for two cells, it's the same for two planets, it's the same for two animals. So this is a universal constant. And the force of gravity is equal to that constant times the product of the masses divided by the radius squared. Okay. All right, so for instance, this object, and if using this formula, if you find that this object attracts this object with a force of 50 pounds, what Newton's third law says is this object will attract this object with a force of 50 pounds. Okay. So each object attracts the other object with a force of equal magnitude. Okay. So for instance, here's an interesting fact. So let's say if you weigh 150 pounds, what does that mean? The Earth attracts you with a force of 150 pounds. And okay, in return, you attract Earth with a force of 150 pounds. Okay. Now it turns out that in nature there are only 4 forces. Okay. Gravity is one of them, and gravity is the weakest force because this is very small. Okay. All right, now here's another interesting fact about gravity. So for instance, so Earth attracts me, right? So right now, why am I not falling back down? So the Earth is attracting me with a force of 160 pounds. The chair is applying an equal and opposite force, and that's why I'm not falling down. Now, if I remove the force that the chair is exerting, then I'll fall toward the Earth. Okay. Now the ground stop. Now here's the point. Now I said every object attracts every other object in the universe. Okay. So she's attracting her, right? Why aren't they falling toward each other? I just fell toward the Earth. You saw that. So the reason is, you guys understand the question? Okay. So the reason is, okay, this constant is very small, and for this force to be large enough, at least one of the masses has to be large. The Earth's mass was large, and so I fell toward the Earth. Okay. The force of attraction between two people is roughly equal to the weight of one of your hair. That's how small that is. Okay. So that's why you don't fall toward each other, but you'll fall toward the earth. Okay? Okay, gravitational force and weight. Okay. The gravitational force is a vector. So for instance, here, Earth attracts me at every location, Earth attracts you towards the center of the Earth. Okay, so for here in the US, I'm attracted like that. So if I went to Australia, that would be the direction of the force. Okay, this is the magnitude of this force is 160 pounds pointing toward the center of the Earth. 160 pounds pointing towards the center of the Earth. Your weight that we talk about, that's just the magnitude. That's just the magnitude of this force. Okay? So your weight is just your mass times gravity. Okay? And what is the value of acceleration due to gravity? Anybody remember? What's G? G is 9.8 meters per second squared. Okay? All right, so now we'll talk about different kinds of forces that you encounter. All right, so this fella is holding up this laptop. The thing about gravity is it never quits. Okay. So here's the force of gravity that the Earth is pulling on this laptop. Okay. And the reason this laptop is not falling is because this fellow's hand is exerting an equal and opposite force in that direction. And the force he exerts is perpendicular to this interface. Okay, and that's why it's called the normal force. Okay. And this normal force is written like that or with a subscript n. Okay. So for instance, you put your phone on the table, the table is exerting a normal force. Okay. And that normal force arises because the atoms compress and it's an electrostatic repulsion. Okay. And that's why you're not going through the ground, for instance. Okay. You'll encounter tension. Okay. So when you talk about tension, a good thing to remember is a stretched rubber band. Okay. So let's say I have a strong rubber band and it's under a tension of 10 pounds. I'm holding it like this. I'm stretching it. What does that 10 pound mean? That 10 pound means this rubber band is pulling this hand with a force of 10 pounds. How about this hand? Same thing. It's pulling with a force of 10 pounds. Very good. Okay. So, anytime a rope is taut, it's said to be under tension. And if it's under a tension of 20 pounds, it's pulling whatever it's attached to with a force of 20 pounds. And in what direction is it pulling? In a direction such that it wants to get smaller. So this rope is pulling this guy at 20 pounds in this direction, this guy at 20 pounds in that direction. Okay? So for instance, there are three forces acting on this object: the force of gravity, the normal force, and this tension. How many forces are acting on this guy? The force of gravity and tension. Okay? All right. All right, often you encounter situations where several forces act on an object. So here's a barge, okay, and here's this tugboat pushing on him. Here's another tugboat pushing on it. And this barge is accelerating in that direction. Okay. Now, a useful thing to do in analyzing such situations is, what you want to do is just draw the essential quantities. Okay? And that's what a free body diagram is. So what we are doing is, we've represented this barge as a point. Okay? There's the force that this tugboat applied. There is the force this tugboat applied. Okay. What is this guy?
Tension?
I'm sorry?
It's not tension.
No, there's nothing pulling on it. Okay, so look at the subscript. It says drag force. That's the drag force that the water exerts. That's the friction force that the water exerts. Okay, and you see, what is the net effect on the barge? Well, the net force on the barge is the sum of these three forces. There is that force. There is that force. The sum of these two forces is that. And the drag force is always in the direction opposite to the direction of motion. Okay, so there's the drag force. So there's the net force, and the barge accelerates like that. All right, so again, what you want to get out of this slide is, what you want is, you'll encounter problems, and you want to draw just the essential features of the problem. Okay, so what we've done is, we represented the barge as a point and shown all the forces. Now this will work only when the forces are going through the center of mass. So for instance, if this tugboat was pushing over here, what do you think would happen? The barge would spin. Okay, so we'll come to that sort of situation later, but right now, so these guys are applying forces to the center of mass of the object. All right. All right, now we'll talk about friction forces. Yeah. Again, like I said, you saw that friction is in our lives, plays a huge role in our lives. It's all around. Without friction, you couldn't stop your car, okay, and so on. Without friction, you couldn't walk, okay, and so on. So let me show you an app first. Okay, so there are two kinds of friction forces, and we want to understand the difference. Static friction forces and kinetic friction forces. Okay. All right, so here's a little app. So there's this box and the surface. The friction forces, as you'll learn soon, depends on the type of surfaces that are in contact. Okay? And the friction forces is a result of the stickiness of the surfaces. Okay, so for instance, if I put super glue on the bottom of the box, what will happen? The friction force will increase. Okay, so it's a measure of that. All right. Now what I'm going to do is, so here, look at this number. I've applied a 90 Newton force. I'm pushing with a force of 90 newtons, but the box is not moving. Why is it not moving? Because there's a friction force acting in the opposite direction. Okay? I apply a force of, oops. Okay, let me do it again. So right now, I'm not applying a force, so the friction force is 0. I applied a 30 Newton force, and the friction force was 30 newtons. I applied a 48 Newton friction force. The friction force was that. This is called a static friction force because the object is not moving. Okay? So you can see that the static friction force can be between 0 and there'll be a maximum value. Okay? It can be anywhere from 0 to that maximum value. What will happen if I apply greater than the maximum value? The object will start moving. Okay? And once the object is moving, then there's still a friction force. That is a kinetic friction force. Okay? And it turns out that kinetic friction force is always smaller than the maximum static friction force. Okay? All right. Did you guys understand the idea of a maximum static friction force? Here's a box. I pushed it with 10 newtons, it did not move. I pushed it with 25 newtons, it did not move. I pushed it with 30 newtons and it started moving. And that's the maximum static friction. Okay. All right. Okay, so here's how friction forces arise. Okay, if you have two objects, no matter how smooth the surface are, if you look under the microscope, it'll be jagged. And if the object is trying to move in this direction, see, these molecules attract each other loosely, and you have to break those bonds to get the object moving, and that's what's providing the friction force. You try and move it in this direction, the bonds are holding you back in the other direction. So the friction force is always opposite to the direction of motion, or the intended direction of motion. Okay. Okay. Static friction forces are denoted by little f. The subscript s tells you it's a static friction force. And you learned that the static friction force can be anywhere from 0 to a maximum value. Yep. And here's the maximum static friction force. The maximum static friction force is mu s times the normal force. Okay. So for instance, in this, when this box is sitting, there is the weight of the box, and there is the normal force. And the maximum static friction force is mu s times the normal force. Mu is called the coefficient of friction. And it measures the stickiness of the surface. So for instance, if I put super glue under the surface, what did I do? I increased mu. Yep. So that's what that is. Okay. Once the object starts moving, the friction force is a kinetic friction force. That's what the subscript K is. And that's equal to mu K times the normal force. Okay, since this guy is always smaller than that, this guy is smaller than this. Okay, so mu K is always smaller than mu S. Okay. And that's what this diagram is showing you. See, this is the maximum static friction force. This is the applied force. There is the maximum static friction force. And once the object starts moving, here is the kinetic friction force, which is less than the maximum static friction force. Okay. All right, so these coefficients are important. Here is a coefficient of, this is the kinetic coefficient of friction. There's the static coefficient of friction. Yeah. So what this says is, so this is rubber on dry concrete. All right, let me show you what these numbers mean. Okay, so this is so let's say this is a 100-pound rubber block sitting on concrete. Okay. Now the normal force is 100 pounds. Okay. Now let's ask the question, what force do I need to keep it moving at constant velocity? Okay, so here's a rubber block sitting on concrete, and I want to find what force I need to apply to keep it moving at a steady rate. Okay, so this is not irrelevant. If you have to push a box around on a floor, you'd have to do this kind of calculation. What force do you need? So if you're moving it, then it's a kinetic friction force. Okay, and this force needs to be equal to that force. Okay. And what is the kinetic friction force? So it's mu K times the normal force. And for rubber on concrete, that's 0.7. 0.7 times 100 pounds. So if you had a 100-pound rubber block sitting on a concrete floor, what you have to do is you have to apply a 70-pound force to keep it moving at a steady velocity. And what the number one says is to get it to move, that's the maximum static friction force, you'd have to apply 1 times 100-pound force. Okay? So that's what those numbers are saying. Okay, so you have a 100-pound rubber block sitting on the concrete floor. To get it started, you need a 100-pound force. To keep it moving, you need 70 pounds. Okay. What does this mean? A metal block sitting on a wood surface, all you need is 30 pounds to keep it moving. You need 50 pounds to get it started. Okay. All right. Now, I mean, all the young people probably don't realize this, because you all have anti-locking braking system in your cars. But I don't know, I'm old enough where I remember when I used to buy car insurance, they would ask me, does your car have anti-locking braking system? Anybody know this? You
I
know.
have a 67 Mustang that does not.
What's that?
Because I have a 67 Mustang like my husband does, and it does not. So
Yeah.
I know, like, what you mean.
Yeah, so you are paying higher insurance on that one.
Well, not really, because it's in our garage, like, stored as an.
Oh, I see. Okay.
So I think that's really good.
Okay.
But yeah, if it was on the road.
All right. So what that is about is the following. Okay. So, okay, you saw this equation before. You don't have to remember this equation. I'm just. Okay. So let's say you're driving. Okay. What the insurance company cares about is the following: how fast can you stop your car? Okay. The shorter the distance you can stop your car in, the less likely you're going to get into an accident. Okay? And that's what they base, everything is based on probability. Okay? So they want to minimize this distance. Okay? So you're going at, let's say, 100 miles an hour, you want to come to stop, they want to minimize this distance. If you want to, so you have this number, you want to make this number smaller, you have to make this number bigger. Okay, friction force is what stops your car. There's the mass of your car. The greater the friction force, the greater the acceleration. Okay, so this is several steps to the argument. And if you have anti-locking braking system, you're using a static friction force to stop your car, not the kinetic friction force. Okay, that's why we talked about rubber on concrete. Okay, so if you have an anti-locking braking system, this is 30% greater. You stop in 30% less distance. Okay, and so that's why they'll give you a car insurance at a lower rate. Okay. Look at the same thing, rubber on wet concrete. Okay, when it rains heavily, you've lost 30% of your braking power. Okay. On a wet road, the friction coefficients are less. Here's another number I'll point to you. Okay. Okay, when you're walking, what is happening? Your joints are moving. Okay. And when your joints are moving, their bone is moving against bone. Okay. If you have too much friction, then you're wasting energy and there's wear and tear. Okay. Look at this. So bone lubricated with the synovial fluid. Very small friction. 1% of the friction compared to rubber on concrete. Okay? This got to last your lifetime. Okay? So whatever nature does, it does well. All All right, here's another example. During a massage, the normal force increases if the massage therapist supports more her weight with her hands. This causes more friction. Okay, so let's say if you want, well, this is if you're getting a massage. If you want a deep tissue massage, so the massage therapist has to push harder to get, okay, and so the normal force is higher. Now, if she wants to move her hand, hand in this direction, there's the friction force in that direction. Okay, the greater the normal force, the greater the friction force. So you put oil to decrease mu k. Okay, so during deep tissue massage, this causes so therapist must support more of her weight with her hands. This causes more friction because Fn is larger. To compensate, a lubricating oil with a low coefficient of friction is used. All right, we use our muscles to exert forces. Okay, and muscles exert forces when they contract. Okay, so muscles cannot expand; they only can contract. Okay. So in our body, we always have pairs of muscles. So for instance, and here's a muscle that's connected to that bone, and there's a joint in between. So when this muscle contracts, this bone is pulled in that direction, and your leg folds. Okay, so this is called a flexor muscle. And when you want to extend your legs, when you want to go from here to there, what you use is this muscle. This muscle is attached to there and there, and it pulls on this. Okay, so this is called an extensor muscle. Okay, and so these muscles are connected to bones across a joint. Okay. Here's another example. Okay, so the bicep is connected to there and there. So when the bicep contracts, your hand moves up. And when you want to straighten your hand, you use this muscle, the extensor muscle, which is the tricep. The tricep is connected there and there. And when this muscle contracts, it pulls this bone down. Okay. Yeah, so there's a blow up of that guy. So when you want to fold your leg, this muscle contracts and the bone moves this way. And when you want to extend your leg, that muscle contracts, which pulls forward, and you straighten your leg. Okay, we have lots of muscles in our body. Why do you think we have lots of muscles? Why not one big muscle? I'm sorry? Good. So what you have different muscles, because of different muscles, what you can do is apply forces in different directions. Okay? So for instance, if you wanted to apply a force only in that direction, you just contract this muscle. If you wanted to apply a force in this direction, then this muscle and this muscle contracts. This muscle and this muscle contracts, and there's the net force. You want to apply a force in this direction, all these guys have to come into play. Okay? This guy's to contract, this guy's to contract, all these guys. And then the net force is in that direction. Okay? So there are hundreds of muscles in the human body allowing forces to be exerted in almost any direction. Okay. And we learned that at the beginning of the chapter, or the beginning of the course, more muscles you're using, the less efficient you become. Okay? Because you see, forces are starting to work against each other. Okay. So do you guys remember what is the efficiency when you're bicycling? I'm sorry? 20%. Okay, that's because you're using mainly these two big muscles. When you're swimming on the surface of water, do you guys remember efficiency? I'm sorry? 2%. Underwater is 4%. Yeah, that's why when they dive. Okay. So, now there are sphincter muscles that are not attached to any bone or anything. Okay, they're circular muscles, and when they contract, they become smaller, and when they're relaxed, and they have functions. So, for instance, the esophagus has you learn in one of the next chapter, has lower pressure than the stomach. The pressure in the esophagus is lower than in the stomach. Okay, so you learned that fluid flows from a higher pressure to lower pressure. So all the stomach acids would get into your esophagus. How do you stop that? The sphincter muscle at the bottom of the esophagus stops that. Okay, it closes that opening. Yep. So, and when you get heartburn, the sphincter muscle is not doing its job. So the sphincter at the lower end of the esophagus prevents the backflow of stomach fluids. Your eye has a sphincter muscle. Okay, it's called the ciliary muscle. So, okay. See, your eye is pretty amazing. This device has only one focal length. It can't change its focal length. Okay. Now, your eye, on the other hand, I can focus, her image is focused. I'll look there and instantly a far off object is focused. Okay. How does your eye do that? It's changing the focal length of its lens. Okay. So if you have an object over here, what is the job of the eye? To get a sharp focused image on the retina. Okay. So when you're looking at far away objects, so around this, the lens of your eye is suspended by these threads called nodules attached to the sphincter muscle. So when you're looking at far away objects, the sphincter muscle is relaxed. The nodules are stretched. The lens is thin. Okay? So when this is relaxed, the lens is thin, and you're focusing far off objects on the retina. Okay, now let's say you bring a book and you want to read this. What happens is the sphincter muscle contracts. The lens becomes thicker, and nearby objects are now focused on the retina. Okay? And all that is done in a flash of a blink. Okay? In the blink of an eye. So your eye is pretty amazing. Yeah, I don't know if anybody's seen this. Okay, so let's say this person has broken the backbone, and you have damaged vertebrae, and you want to give the vertebrae time to heal. Okay, now there are muscles attached to the backbone, and the muscles want to contract. Okay, and they want to compress the vertebrae into each other. Okay, and if the vertebrae run into your spinal cord, they'll do damage to that, the sharp edges. So how do you prevent that?
Not the cartilage between the vertebrae.
Yeah, well, yeah, but if the bone is broken, it's trying to compress, and so you put them in a traction. So you stretch the backbone. And here is a traction system. Okay. So what they do is put pins on the side of the skull, and then they hang weights like that, and the backbone is stretched. Okay. And it gives time for the bones to the vertebrae to heal without causing damage to the spinal cord. Okay. Has anybody seen anything like this? You've seen it? Okay. Where? Okay, so.
No, I got to see patients like that, broken femurs too.
Mm-hmm.
With the pulley system and
Yeah, I'll show you that in the next. So a patient is lying like that for months.
Yeah.
All right. So here's the femur system that our friend talked about. Okay, let's say you break the femur. Well, this muscle that's attached there, the muscle that you saw a second ago, this muscle wants to contract. And what it wants to do is bring that broken femur against the other femur. Okay, so this muscle wants to contract, run this broken femur into that, and then you don't heal properly. So what you have to do is you have to pull these two bones apart so they heal properly. You have to apply a force against this muscle that is pulling. Okay, and here's a way to do this. So there are two things that you're doing. You're just supporting this weight so it hangs like that. And then what you do is you put pins in that bone and attach a weight like that. And so you're pulling this bone apart against that muscle that's pulling it. Okay. Again, I guess whatever time it takes to heal, a month or so. Okay. Okay, now we'll talk about the effects of rotation, okay, that forces have. Okay, so forces can give you linear motion, and they have their effect of rotation is measured in something called a torque. So forces can cause linear motion and rotational motion. Okay. The effectiveness of a force in producing angular acceleration is called torque. Okay. So we'll look at that. So for instance, you all used a wrench. You apply a force like this, it's easier to unscrew the nut. You take the same wrench, and when it's there, the effectiveness of this force is less. Okay. So for instance, if you applied a force here, it's harder to loosen the nut. Okay. So what is it? What is happening? So the torque on the wrench is the force you apply times the lever arm. The lever arm is this distance. Okay. When the lever arm is large, the torque is large for the same force. For this force, there is the lever arm. See, the lever arm has gotten shorter and the torque has gotten shorter. For this force, that's the lever arm. Okay. And so in this configuration, it's very hard to unscrew the nut. Okay. All right, so you're opening this door, you apply a force like that, there's the hinge, and there's the lever arm. For this force, that's the lever arm. You push the door in the middle of the door, it's hard to open the door. Okay? And now that's why they don't put it on the knob here, they put the knob at the very edge, so you have the greatest lever arm. Okay? Okay. By the way, so these are the conditions for equilibrium. Okay, so what this shows you is the following. Okay, so let's say here this is true for extended objects. So if you have, there's the center of mass. If you apply these two equal and opposite forces, this won't move. I apply equal and opposite forces. Will this object move? No. I'm applying the same equal and opposite forces. Will this object move? It won't move, but it'll spin. Yeah, okay. So now the torque is not zero. That's the difference. Here torque is zero. Torque is denoted by tau. Okay. This is zero. This is zero. This is not zero. Okay. So the conditions for equilibrium are the net force should be zero and the torque needs to be zero. Okay. So for an object to be at rest, those two conditions need to be satisfied. All right, so we'll do one example, and you just have to know, you have to have a sense for it. You just follow the numbers, okay? And you'll learn something surprising. Well, you might know this, but anyway, we'll go through this, okay? So here's what this is illustrating is, so this person is holding up a book, okay? Or it could be, so you're holding up a bowling ball or whatever. Okay, so let's look at the forces. Okay, so here's the weight of the book. Here's the weight of the arm itself. The weight acts at the center of gravity. Okay, so what these forces want to do is, here's the hinge, and these forces want to turn the arm in this direction around the hinge. Okay, so when I'm holding this force is wanting to turn my arm like that. So what is preventing that from happening? Okay. If I hold a heavy object, I can't hold it. Okay. It will fall down. So this muscle, the bicep muscle, is pulling on this arm in this direction. So this weight wants to turn it clockwise, and the bicep muscle is wanting to turn my arm counterclockwise. So when that torque is balancing this torque, I can hold my hand. Okay. All right, so that's what we mean clockwise. When you're in equilibrium, clockwise torques need to equal counterclockwise torques provided by this bicep muscles. All right, now here's the deal. You saw that torques are greater the lever arm, greater the torque. Okay, torque is force times lever arm. Okay, perpendicular distance. Greater the lever arm, smaller the force you need to apply. Did you guys understand? Okay, smaller the lever arm, greater the force you have to apply. Okay, so this is very important. All right, let's go back to our example. Okay, so these are providing the clockwise torque. See, these guys have large lever arms. What is the force that is providing the counterclockwise torque? The bicep. And structurally, these muscles have to be connected close to the pivot point. The lever arm is very small for that. So this force has to be quite large. And that's what we're going to show you. Okay? So all the muscles, the forces that you're applying in your muscles are quite large. You guys understand what I'm saying? Okay, so here's the clockwise torque, and I'm going to go through this fairly quickly because I just want you to remember okay, so the weight of this guy, so here the weight, mg is the weight, the mass of the arm is 2.5 kg times gravity is 25 newtons. The weight of this is 4 kg times that's 40 newtons. Okay, so there is that and that. So 25 newtons, and the lever arm is 15 centimeters. 40 newtons, moment arm is 40 centimeters. Okay, and that is balanced by the bicep force, which is providing the counterclockwise torque, and the moment arm is 4 centimeters for it, 2 inches. Okay, so you can calculate the force of the bicep, this number divided by that number, and it's 484 newtons. So the bicep is applying a force of 484 newtons to lift the weight of total weight of 40 plus 24, 16 newtons. Okay, what we're saying is to lift a force of 60 pounds, your muscles are applying a force of 480 pounds, 8 times greater. Okay, so there's something called a mechanical advantage of machines. That is the output force divided by the input force. So in this case, the output force was 60 newtons, roughly, this plus that, and the input force was 480 newtons. 1/8. That's more of a mechanical disadvantage. So for every pound you lift, you're applying an 8-pound force. Okay? And the reason is because structurally the muscles had to be attached very close to the fulcrum. That's why you have to do that. Okay? And also there's another fact that your muscles can't contract too much. So okay. So the bicep is said to be at a mechanical disadvantage, as are most muscles in the body. Okay? So your muscles can apply a large force, but they're at a mechanical disadvantage. Okay, so let's now look at good posture. Okay. So good posture is, okay, so here's a fulcrum. Okay, this is bad posture. Okay, I'm not falling down, but what is happening now? Okay, so my torso wants to fall down. Okay, so the weight of my torso is applying a clockwise torque. I need something to apply a counterclockwise torque. Okay, so when I'm forward, there's the fulcrum. This weight wants to topple me over. Okay, so the muscles in my back have to prevent me from toppling over. So this is providing the clockwise torque. These muscles have to provide a counterclockwise torque. And you see the lever arm for the back muscles are very small, so these forces have to be large. So if I'm walking like that, my muscles are constantly contracting. Okay? Now if the center of mass of my torso is right above my fulcrum, now my muscles are not doing anything. Okay? So good posture is very important. All right, now we'll show you how to lift an object properly. Again, so that was the promise to begin with. Okay. So let's say you're lifting a large box. Okay, if you lift it like this, if you lift it straight like that, here's what's happening. Okay, so this box is here's the fulcrum. This box has a lever arm. It's trying to rotate you in this direction. Your torso is also not helping. It's also trying to fall down. So your back muscle, what it has to do is to lift your torso along with this thing. Okay? So that's a double whammy. You try to lift like that. Okay, now your book doesn't do a good job on this diagram, but here's the correct way to lift. Okay, so when you're lifting, what you want to do is squat down, have the box has to be past your knee. Now you're lifting around your knee. Okay, so the box is trying to topple you like this, but you see now the weight of your torso is helping you, providing you with the counterclockwise torque. Your back muscle, also the lever arm is large, so it doesn't have to apply a large force. In addition, now your leg, which is a strong muscle, will provide the counterclockwise torque. Okay? So, if this box is close to your knee, your torso weight and all that, and this force is very small. Okay? You don't want to strain your back. Okay? So that's the correct way to lift objects. All right. One last concept you have to learn, and then we'll do the quiz. So let's do this. Here's a glass of water. I'll go get a handful of dirt and mix it in the water. Now, if I let this glass sit, what will happen to the dirt? It'll settle down to the bottom, right? It settles down because of gravity. Okay. Now, if somehow I could increase gravity, what would happen to the dirt? Would it take longer to settle down, or I'm sorry? It'll settle down faster. Okay. Now, the smaller the particles, the longer it takes. Now, let's say this is cells in your blood, in your plasma, and you want to separate the cells. You want it to settle down, okay? And you don't have forever to wait, okay? So you want to somehow increase gravity. Well, how the heck do you increase gravity? Okay? So let's figure that out. So here's a circular road. Okay? And if you go at a constant speed in a circular road, so this is what the speed is constant. Are you accelerating? Very good, very good. Why are you accelerating?
The direction.
The direction of the velocity is changing, and hence you're accelerating, and so you're applying a force. So you're accelerating in this direction. So to make anything go in a circle, you have to apply a force in that direction. And if you're not able to apply that force, that thing will go straight. It'll appear like it's going away. Okay? All right. So what we're going to do is, this is what an ultracentrifuge does. Okay? So you take blood in there, and you want to settle all this stuff. And what you do is you spin it in a circle. Okay? So if you spin it fast enough, you have to apply a large force in that direction. Okay? And if you're not able to apply that large force, if the liquid is not able to apply that large force, all that stuff will settle down. Okay? Here, there are ultracentrifuges that spin at 150,000 revolutions per minute. Okay? And this distance is about 5 centimeters. So this distance is about 2 inches. So this acceleration is v squared by r, and that's calculated here. V is calculated to be 785 meters per second. And if you calculate the centripetal acceleration, that is 1.2 million. Okay, so 1.23 into 10 to the 6 into 10 meters per second squared. So that is g. Okay, g is roughly 9.8. Okay, so this acceleration has to be 1,000,000 times greater than g. You have increased, remember, you've increased just g by a factor of 1,000,000. That thing will settle down in a jiffy. Okay, so that's why if you put stuff in a ultracentrifuge and spin it like crazy, you've increased g by a factor of 1,000,000, and the fluid is not able to exert that force, and all that stuff will settle down. And of course, the heavier stuff will settle at the bottom, and then the lighter stuff inside. Okay, so that's the idea of a centrifuge. You're making things settle down faster by increasing gravity artificially. Okay. All right, guys. So that finishes this chapter.